Hello, this is Uncle Johnny El Diablo, and I'm here making my second video on my YouTube channel for what my original purposes was to teach engine theory, mechanic work, etc. If you want to know my history and background, I believe I included most, if not all of it, in my first video. In my original new YouTube endeavor, mechanical training. Today we're going to talk about a few things, and what I'm going to talk about today is the law. Now, I'm not referring to the blue lights in your mirror because you didn't have your seatbelt on or something. I'm talking about the law. The law that the powers that be, the masters of the universe, created or established to make life possible and to govern all life on the planet and throughout the known universe that we know of. And those are the laws of physics. An object in motion will stay in motion unless acted upon by an outside force. Law of thermodynamics. Pressure is always equal and constant throughout a contained vessel. There are several laws of physics. You need to read up on them and study them because they apply to everything. And when you are a mechanic or a technician or a designer or engineer, everything must comply to these laws. There are a lot of people in the world who say, this is a bad engine, that's a bad engine, that's a bad engine. That's not really the case. If you have a great design and it is made out of the finest materials money can buy, which throughout diesel engines was traditionally the Caterpillar and Mack. They used very high quality steel in their engines, their parts, everything. Even the outside contractors or suppliers that made parts for them had to comply with certain criteria, and they required high nickel content in their steel, and so their blocks didn't rust real bad, and they didn't flake away, and they wore very well. They had a very good longevity. In the gas engine market, traditionally Cadillac, Buick, Oldsmobile, Pontiac, and I'm an Oldsmobile fan myself. I've had a couple of them. They have about 3 to 5% more nickel steel in their block that the blocks are cast out of, and so they wear very well. And they also used traditionally a little bit longer connecting rod length, which reduces lateral or side thrust from your major or minor thrust surfaces. Now, Caterpillar also uses good steel, or used to use good steel in their blocks, and I'm sure they still do. Of course, Cat quit making diesel engines, from what I've heard, and I haven't heard anybody say anything to the contrary. But you'll notice that, like on the 3208, for example, it is what they call an integral cylinder. In other words, it does not have a removable liner. This is traditionally gas engine construction. And 3208s were put down for that. That's not really fair. That doesn't cause the engine wears out because of oil that is contaminated or bad oil. It doesn't have the lubricity or lubrication qualities that Cat recommends. You know, people put cheap dime store oil in a motor because they don't like it. We're only inviting danger and injury. The nickel steel in it is high quality. The short rod creates a wedging effect, which is what causes cylinders to wear very badly. In hot rod engines, people would use a chrome moly first ring, and they would use a cast or ductile iron second ring. The surface finish required to seat those two rings is very different. If you use a fine finish, it will not hurt the moly, and it'll be enough to seat the moly ring, the top ring, which will withstand heat, etc., much better than a regular. But it's delicate. It does not like a rough cylinder surface finish. It will chip out the moly unless it's a pure chrome, which is bad on that also. And it's too fine to seat in the second cast iron or ductile iron ring. So when you use mixed match ring sets, you have to understand this. If you went to school and learned physics and metallurgy and were professionally trained at a trade school or vocational center, you'd understand this. You cannot read a hot rod magazine or watch a video and simply become a mechanic or a technician. It takes much more than that. when you understand this, you understand they're not really what you call bad engines. There are some engines that are bad designs. They were defective, they were just a bad design. It doesn't matter who built it and how much pride they took in it, and it's a bad design. It will always be a bad design. If an engine is a good design, made out of good materials with the finest of workmanship and people assembling it, machining it, putting it together, it'll be a great engine. So when you say that an engine is bad, there may be a reason for it. It may be a very good engine design, and it may be made with the finest quality materials, but if the workers didn't get a raise and decided, well, we don't care, we're not going to buy one, we'll never own one, we'll just throw it together, it's going to be a bad engine. For instance on that would be the Cleveland Ford engine. It had a history when it first came out of main bearing problems. Well, this is because the workers didn't get the conditions and wages that they want. They went on strike, and they didn't even tighten the main cap bolts, and so they shut down the Cleveland plant. And when they reopened it to start making Cleveland engines again, they had a robotic machine which put all the caps on at the same time, and the machine torqued them, and that eliminated the main bearing problems from the factory. That's because of piss poor workmanship from workers. That has nothing to do with the material, the engine, the quality in the machining, or the engine design. It was a good design for what it was doing. It was basically a factory hot rod engine. If you know the history of the 351 Cleveland, it was a powerhouse. It was a factory hot rod, even though it may not have looked like one. It was and had the potential to be a super drag strip engine, a pro stock engine, and they have a very good history of that. But when they first come out, they had a lot of problems with main bearings. Well, that was workers that did that. So don't say that, well, that's a bad engine. Well, that was a really good engine. Well, that's a bad one. There are reasons why things are good and bad. It does not have putting a Ford emblem on a bad engine doesn't make it great because it has Ford. And I'm Ford blue through and through. I love Fords. Well, if you have a great engine and you put a bad name on it, it doesn't make it a bad engine. It just means you give it a bad name. You could take the best engine in the world and piss poor materials, design, quality of machining, assembly, craftsmanship. These are the trademarks of a good or a bad engine. Now, there are some bad engine designs, there's no doubt about that. But today's video is the laws of physics. When a piston goes down on a gas engine, it creates a vacuum because the rings seal, and the air will eventually leak through the end gaps. But this takes time. Well, it doesn't have the time to do that because of the rotation of the engine. So it creates a vacuum. And this is when the intake valve is open. This is what draws air in as the air goes past the carburetor. It is mixed with air from air bleeds, which are also anti-siphons, and pulls mixture out of the carburetor. Now, everybody will complain about what they call a quadrajet carburetor. It's a very good design. And it's very flexible, very forgiving design. But it added air in several different stages to emulsify or break down an amount of fuel into particles. And the finer and more particles any given amount is, the less time and heat it takes to vaporize them and burn them. When you have people always over tighten them and it warps the body, and then they leak air and the gaskets really don't seal internally. And they'll say, well, it's called it a quadrant junk. Well, it's not a quadrant junk. It's because you didn't know what the hell you were doing. And you destroyed it. You ruined it. People will put oil from a pin oiler on the throttle shafts. And that's a good idea. But it's counterproductive. Because the vacuum, or less than atmospheric air, and air fills that, blows through that. And because it was not a sealed radial bearing, it was a bushing, or just a factory machine surface in the throttle body, oil does lubricate, and that's a good thing. But the air pulls that oil out as the engine is running, and dust is always in the engine compartment, and it mixes it and makes a grinding compound. And it's actually, in the long term, it turns counterproductive. It chews and you get tremendous, and then it doesn't meter fuel properly because you have air gaps. And bad gaskets, over tightening them, ruined a lot of very good quadrajet carburetors. That has nothing to do with it being a bad design. It has to do with you don't know what shit you're doing and you screwed it up. So don't blame and call it a quadrant junk. It is not a quadrant junk. It's a very good carburetor. If it wasn't good, Holly wouldn't have come out with the spread bore series, which was their way of copying the quadrajet with a larger secondary than primary venturis or throttle plates. The Quadrajet was very innovative. It's a very good carburetor. I love them. The power piston spring gets very weak in them, and then they don't push the piston up, and so it doesn't richen up the fuel mixture, and they'll backfire and miss and get flat spots and soggy spots, and people will blame it on the carburetor. No, it's heat and time. It weakens the spring steel that the little small spring in the power valve is made of. One of the main problems with the Quadrajet is the power valves will stick. Now you can tap it and jar it loose, and you can actually take it apart and clean it with steel wool you could use, or a Scotch-Brite pad, or crocus cloth, and you want to polish it and get all the burrs and stuff off of it. But a new spring, and they made several different ones, there are different lengths, different tensions, and when they get weak, the carburetor will not work right. And it's not because it's a bad design, it's because time has taken its toll. That's called metal fatigue. Holley is a good carburetor, and I've had several of them. They have a bad problem when they backfire. The power valve is a vacuum diaphragm, and vacuum diaphragms tend to blow when it backfires good. And some people will say, well, it's a good carburetor, but they constantly blow power valves. Well, it's not because it's a bad carburetor. That's just the way things are. Holleys have a brass float, and some people will go to a parts store and they'll get a float for a gas engine, a Quadrajet, and they'll sell you, well, this is the high performance version, this is a brass float. Well, that won't work. Put a safety pin and then put a nut, a large nut on it, and drop that float down in a glass of water. Now, that for all intended purposes, that water would be called a constant. And the paper clip, that's the word I was looking for, paper clip, and the nut, those are constants because they don't change. And when you drop it in the float and it sinks to the bottom, it's because it is not buoyant enough. You use the same paper clip and the same nut with a factory replacement nitro-Philly float for a Quadrajet, and it'll float. This is the reason why when you put an aftermarket brass float in a Quadrajet, it will flood. Now, that design works great in a Holley because if you'll notice inside of it, it's a bigger brass float. It has more leverage from the fulcrum to the pin, so it has more leverage to operate the needle and seat. And there's also an assist spring. So don't say that something is bad when you don't really know what you're talking about. My main intention, I had to be a great gas engine mechanic, and they picked out of about 50 applicants, 18 that were the best, and I was the number 1 or number 2 pick for the diesel program. You had to be a great gas engine mechanic and successfully pass a 2-year training program before you got the last year in your diesel program. And so I was great at both. I never was beaten or excelled in the classroom or in the shop. I'm trying to teach you. I'm doing this for free. I don't make any money doing this. Pay attention. You'll learn something. It takes time. In a diesel engine, you traditionally have what you call an under-square design. And what that means is that the piston bore diameter is less in inches than the length of the stroke. I don't remember the exact diameter of a 71 series Detroit diesel 2-cycle. I think it was 4.5 or 4 7/8 inch diameter and had a 5-inch stroke. Your Max and your Cats and your Cumminses, your 855s, you would have, a 5 3/4 inch or 5.5 inch cylinder bore diameter and a 6-inch stroke. And some of your Cats have a 6.5 inch stroke, and I think your new ISXs have a 6.5 inch stroke. That is undersquare. That is made for lower RPM and more torque, more twisting force on a shaft. Horsepower engines are traditionally what they call oversquare. In other words, they'll have a 4.5 inch bore and a 3.850 stroke, or 3 7/8. The only square gas engine that I know of, and I love the particular engine, is a 400 Ford. It is not a 400 modified. It was never modified. It was made from the factory from the very minute, a 400. And that has a 4-inch bore and a 4-inch stroke. It is a square engine, same diameter bore in length as the stroke length. A 460 has, I think, a 4.25 to a 4.5 inch bore, but it has a 3.850 stroke. It has less, it is over square. Ironically, it makes more torque and horsepower than a 400, and it traditionally uses less gas. I used to run them in ambulances, and with 410 ring and pinion, and it was a heavy ambulance, you almost get 17 to 18 miles to a gallon. You always got at least 16. 12 to 14 is pretty much the best you get out of a 400 Ford. Just because an engine is bigger does not mean it will use more fuel. In the diesel engine industry, people will always say, well, I'd rather have a 350. You know, they don't make a lot of power, they don't tear up stuff, and they burn less fuel than a 4 1/4. Not necessarily. Not necessarily. 4 1/4 cat had the first generation, whether it was a B and A, B, or C, it had a set of flyweights and cone on the front timing cover, which varied the timing. Cummins came out with the step timing setup, which used basically a hydraulic valve lifter that was collapsible on top of the injector. And at idle or below 70 psi, and it's variable, you can adjust it. Most people don't know it, but you can. There's a 49 state step timing box and another one. And some of them have to add a bleed line because they didn't have a diaphragm. They just had a disc with a machine, an interference fit. And if you don't have a return line, it builds up pressure eventually and equalizes, and the valve doesn't work. Not because it's defective, it's just you should have had a return line on it. That's what makes it work. And that will admit or let oil drop off of the valve lifter, and when it collapses, you get retarded timing. Once it goes past, generally it was 70 psi on the PT pump, it would drop the pressure on the oil channel to that hydraulic valve, to a hydraulic injector, and it would fire later. But that was fine because at that pressure, it was already injecting way too fast anyway and needed to be retarded for timing. On a Cummins, even though it is what you call a constant, you have a roller cam and you have a cylindrical injector, and it fires whatever you set the thickness of the rocker, the cam followers. That's how you adjusted them. On your V8 engines, they used an offset cam key because they didn't have rocker boxes. And on your traditional 855s, 855 cubic inches, they use different thickness gaskets or gasket stacks to move the rocker box to vary the injector timing. This also varied the intake and exhaust valve timing too. But at idle, you're only getting a drop of fuel in a Cummins cup, and it's almost at the end of the injection stroke before it finally traps that, can't compress the air anymore, and squeezes the fuel out through the little holes in the tip and atomizes it and fires. When you pour the fuel to it, the cup is half full, a quarter full, or 3/4 full. The more it's full, the sooner it will run out of space to compress the air and start injecting fuel. So as you crank the fuel on a Cummins, it begins to inject sooner. So it varies. It actually increases injection advance. That's good to a point, but when you get the injection advance too much, it's actually pushing down on the piston before it's the right time to, and it kills your power. So generally on a Cummins, when you crank it up the horsepower, you lower the compression ratio and you retard the timing. Now step timing gave it two distinct steps. So as the fuel would get up, it would retard the timing so you could pour more fuel to it without over advancing it. Detroit's have cylindrical unit injectors, and they are rebuildable. They made two different popping pressures. I told that in the previous video. But it doesn't have, not all the injectors are the same. Some of them have different helixes ground into the plungers. And so as you would increase the RPM, it would also increase the beginning of the injection. And that's good for efficiency, but when you're pulling and the RPM is down, you don't want over-advanced injection timing, because that's not only pre-ignition, but it's pushing down on the piston before it's the right perfect time to do it, and that kills your power output. So if you get your timing on a Detroit unit injector wrong, that will hurt your power. The only way to really test that would be on an engine dyno or on a chassis dyno. And now there are books where other people have done this, and the Detroit factory and Cummins factory and Cat factory also have specs on this, if you can get access to them, that tell you the optimum static timing for perfect engine performance. But fuel is injected in and it burns. Well, it's injected in a diesel injector under high pressure. And give or take, high pressure injectors are all usually around 1200 psi, give or take. And when you squeeze that through a little 2,000-inch hole, and there's 6 or 8 of them, that shatters the fuel into thousands of particles. And those small particles absorb heat very quickly and vaporize, because liquids don't burn, and the gas immediately ignites. It can't all ignite at once because it all isn't injected at once. It's injected over a period of crankshaft degrees of revolution. In a gas engine, the fuel is already in there on the compression stroke, and so you can't inject fuel, and you could have mechanical timed injection, but there's no oil and gasoline to lubricate, and the pump would burn up. But on a diesel, which is what we're particularly talking about here, the fuel is injected over 23-30 degrees of crankshaft revolution, so it's not all in there on the compression stroke. None of it's on there in compression stroke, and it will start to inject. If the static timing is, say, 19 degrees, there'll actually be about a 2-degree lag of crankshaft rotation before it actually starts to do it. The more holes and the smaller diameter, the finer you break the fuel, and a given amount of fuel, into drops or mist, a spray, and that vaporizes quickly. It absorbs the heat, vaporizes into a gas, and immediately, because of the excess heat past the point of ignition, or what they call a flash point or ignition point, ignites. This is what makes a diesel engine run. Now, your modern electronic engines vary with a solenoid and a computer and sensors, etc. They vary the beginning of injection and the end of injection. So they can not only increase RPM, they can move the timing curve around. Older mechanical engines didn't have that flexibility, so they could only go to a certain power level. But they're EMP proof. They're very crude and rudimentary. They're very simple and very reliable. There's no computer to go bad, no sensors. And I was trained as an old school mechanic, all mechanical stuff, and I like that. There's nothing wrong with it. And the bottom line is, Detroits are made to be in front of a boat prop or a torque converter. The V8 Cummins and Cats are their manufacturers' designs to compete for markets that Detroit had locked up. I'll go into more detail on this, but I wanted to explain to you the laws of physics. Detroit, the more compression you have, people think you get more power. That is not true. The compression ratio is there for one reason. At a certain speed, as the air is compressed, and air has some degree of mass, it's very light, but it has some degree of mass, it heats up very quickly. It's a gas. It's not a liquid. It's not a solid. There are three forms of matter: solid, liquid, gas. They heat up very quickly, and that heat is what evaporates the liquid fuel spray particles into a gas, and they start burning. And as the engine rotates, it continues to inject more until the end of the injection stroke occurs. They instantly vaporize, and once the fire starts, fuel sprayed in is just instantly vaporized and starts to burn with it. And so different injectors make a big difference on the power of a Detroit, more so than a Cummins or a Cat, because the Cat has plungers in a separate, it looks like a small little engine. It's actually pistons mechanically driven by the engine on a roller camshaft, which moves the plungers. And the fuel rack, controlled by the governor, is what times the intake and closing points. Now, a lot of your Bosch pumps, like on a Mack or Cat makes it, has their own made, they have static timing. It doesn't, most models, and probably all of them that I've ever worked on, had the same static timing. If you set it at 19 degrees, that's where it started all the time. The length of the injection stroke was determined by the rotation of the plunger and the helix ground on it, controlled by the fuel rack and the governor to control RPM and fuel delivery. Cummins does it completely different. I do like the Cummins system, but it has a very bad drawback. It over-injects the fuel. And people will think that on a Cummins, well, we'll just put in a smaller button and that will crank up the fuel and we'll get more power. No. That can be the case, but it's not always the case. If you over-inject it, you're actually killing the power on the engine. Number two, changing the button does modify the basic fuel pressure. And everybody thinks, well, what's a bigger button? Well, pressure is equal. It's just study the law of physics. It's equal and constant everywhere in a system that's closed once it's stabilized. Now, a restriction will cause it to take time to build up past that restriction, but it will still eventually equalize to an equal pressure. That's fluid dynamics. You can read a book and learn that. You don't have to go to college to learn it. I learned it in vocational school. We had classes on it. The smaller diameter button on the Cummins custom rating system, which increases fuel delivery or line pressure, it does that for a reason, and it isn't because it's a smaller button. The pressure is equal and constant. It doesn't make a damn bit of difference. The smaller the button, the farther the fuel has to go to get past to low pressure. And so the smaller button around the circumference of the button surface area, the more area it has to travel to get to low pressure, the more time it takes. And since the time interval is changing, the smaller diameter button it takes longer for them, and so the pressure increases. When you put a larger diameter button, there's a much smaller area it has to travel to get to lower pressure, and so in that given period of time, the smaller surface area bleeds off more pressure and lowers the pressure. It isn't because the smaller diameter recess in the button gives it more pressure. It does, but only because when it moves a thousandth of an inch, the smaller diameter, there's more on the barrel assembly that it has to travel to get the low pressure. And on a larger button, it's only having to travel just a very small amount to get the low pressure, and so that small amount in a given period of time leaks off more pressure. That's how the Cummins custom system rating. Nobody's ever explained that on a YouTube video, so I'm telling you. If I had a piece of paper, and I'll probably draw one out and show it to you at a later date, that's why. Pressure is always the same and constant. To truly vary the pressure, you'd have to change the pressure regulator. Now there's a PT pumps, pressure and time. There's a PTR and a PTG. In one system, it goes to the governor first, then to the pressure regulator. In the other system, it goes to the pressure regulator, then to the governor assembly, then out through the fuel solenoid and to the injectors. They're basically the same, but they're plumb different. They're drilled, and the passages are different. But that's how that works. The smaller diameter button will increase pressure because it has to travel a larger distance. Even though it's a very small amount, it makes a difference when you have 200 or 180 to 250 psi in the fuel rail or inside the pump housing. On the pressure side, the rest of the pump's basically atmospheric pressure. But when it travels a larger distance, it can't bleed off as fast. It takes more time to get across a larger distance, so the pressure goes up. With a larger diameter button or a bigger number button, the recess is bigger, and so it's already pretty much uncovered most of the space, and it only has to travel a very small amount, and in a given period of time more fuel is drained off, the pressure lowers, the horsepower drops. That's how it works. It isn't because of pressure is constant and equal, and the laws of physics never change or modify. Everybody will say, well, that smaller little recess there, the pressure acts on. No, it acts on a small diameter button the same as it does a big diameter button. It's the distance passing the barrel sleeve with the larger button. It travels a shorter distance and drops the pressure. It has nothing to do with the laws of physics, and pressure dynamics are constant. If I had a picture, I could show you and explain it much easier. But this video is getting way too long. It's almost 30 minutes. And I'm going to start writing down some stuff that I hope this has helped you. And study the laws of physics. That's why compression ratio heats the air. Once that air is heated, it starts to immediately cool. Any additional compression ratio that's not needed to vaporize the fuel, whether it's gasoline or diesel, is consuming energy to compress, and that kills your horsepower. On most of your Cummins, they retard the timing, cut the compression ratio, and modify the fuel curve to increase horsepower. Everybody thinks, oh, a 400's got more compression. No, it actually has less. 444's only had about 14.2. 400's had about 16.1. 350s had 18 to 21 to 1. A lot of your Macs had 23 to 1. More of your modern Macs are around 16 to 1 compression ratio. Cats, I can't really say, I don't know right offhand, but increasing your compression ratio doesn't increase horsepower in a diesel engine. In a gas engine, it also consumes power, but the increased compression ratio vaporizes fuel. It creates more heat in the compression stroke, which vaporizes a larger amount of fuel. And if you get in more fuel, you make more, and burn it efficiently, you make more power, but it takes power to do that. BMP, or brake mechanical horsepower, BMHP, that is the maximum amount of horsepower an engine can make regardless. Then it takes horsepower to run the camshaft. When you put big valve springs on a gas engine for high RPM, because that's the only reason to keep the valves from bouncing and floating, that takes a lot of horsepower. It takes more energy to rotate the camshaft against that. Roller cams reduce a large amount of that. So roller cams increase horsepower even with the same profile on valve overlap. They reduce horsepower that the engine is using to operate, so the horsepower goes up. It's not so much because it's roller cam, even though it does it for a reason, and that's the law of physics. Compression ratio takes energy. The higher the compression ratio, the more energy. You take, say, a 500 horsepower engine, and you're going to lose about 7 to 8 horsepower running the cam at, say, 4,000 RPM in a gas engine. you're going to consume another amount of horsepower for the alternator, the water pump, and the oil pump. This is what they call corrected horsepower. The engine may actually make, or the chart may say, well, it's a 400 horsepower engine, but you're only going to get about 338 to 357 at the flywheel. And through your drive line and rotational loss, frictional loss, rotational drag, you're going to lose another 10 to 15% of that. You may only get about 220 at the rear wheels. So you need to understand this kind of stuff before you actually start messing with an engine. I'll get more specific in that as time goes on. This will be a long process. It's just like going to school again. You have to learn. You know, when you come out of the womb, you can't do anything. You can't even crawl or roll over. And you slowly take steps and you learn. And mechanic work or physics or engineering, everything is the same. To a point, mechanics are low-level engineers, if they're really mechanics, formally trained mechanics. Just removing something and replace it, that's parts changing. That's not being a mechanic. A kid can replace a part, but he still doesn't know what he's doing or what's going on. So you need to understand that. This video is 31 minutes long. I got to go. Hope you learned something. I'll see you soon.